Dr. Gabriele Hegerl is a distinguished climatologist and professor of climate system sciences in the School of Geosciences at Edinburgh University. She has a high international standing for her work in climatology, climate variability, climate extremes, and climate change over the past millennium. She has brought about continuing innovative scientific contributions that enable the detection and attribution of anthropogenic climate change, and her work has helped to clarify the causes of global climate change, and as a result, enable significant progress in international climate policy. Dr. Hegerl serves on a number of national and international collaborations. She was the contributing lead author for an important chapter on understanding and distributing climate change for the Intergovernmental Panel on Climate Change, IPCC, Fourth Assessment Report in 2009, and lead author on the Fifth Assessment Report. In 2016, she was awarded the Hans Zegers Prize for her groundbreaking research in climatology, and in 2017, she was elected a Fellow of the Royal Society. While accomplishing all of this, Dr. Hegerl has advocated for the role of women in science and has found it important to encourage and support a diverse set of colleagues. She has been vocal about the need to raise consciousness to the importance in balancing family and work, and that an unorthodox work hours do not mean a lack of commitment. Please join me in welcoming Dr. Gabriele Hegerl.
Good morning. Good morning. Before Darsa sits down, Darsa, stand up again. Darsa is wearing the data. Actually, I'm going to talk about this. One of my colleagues has visualized climate change so it changes from the top to the bottom, getting warmer. So it's a great honor to be here and talk about to what extent do we understand climate change and how can we project it forwards. I hope to share my fascination with understanding why climate changes and why it has changed in the past, why it's changing now, and how these amazing planet's systems work together. So, and that's a seal on the east coast of Scotland where I live in the moment. And the subtitle of my talk would be Climate Change is not a belief system. So it's not something you believe or don't. It is scientific evidence with its uncertainties, but it's a science and not a belief. So before I talk about the observed record that we just saw so nicely on Darsa's dress, I would like to introduce you how it's made. So you have these, when we try to measure if the planet has changed its large-scale global mean temperature, we use instrumental data that we have collected over a long time. So we have some idea how climate has changed back to the 1850s, and we are going back even further now in many projects. And we also have paleoclimate evidence that Richard Ali has talked about earlier. And so on the, do I do this? No. On the right and bottom slide, you see a typical measurement device for surface temperature. So it's a little white box that avoids the thermometer inside being heated too much by the sun and being kind of constantly shaded. So that covers. That's the way land surface data have been taken for quite a while now, from over the 19th century onwards. And we have, over lots of places on the planet, we have these data. People have measured temperature and have been fascinated by measuring temperature over a long time. And over ocean, the sailing boats and then later the steamers have been taking the temperature of the sea surface. And they have been doing this in a variety of devices. So you see a collection of wooden buckets at the top, which is which basically you hold them overboard and then pull them back up again and stick a thermometer in. And people have had a lot of interesting physics and fun with trying to correct for the small bias you get by just waiting a little bit before you stick your thermometer in. So the wooden bucket will cool a little bit less than the canvas bucket. So there have been some interesting attempts to correct for long-term changes in how the data worked. And so over every point on the planet, so if you look at your global map here, people have collected the data in little boxes and aggregated and averaged. So they have looked at how this particular station that has this white box around it deviates in every given year from the average over a long time period. So like 1960 to 1990, for example, is this year an unusually warm or cold year? And then they aggregate it over these little boxes and then plot and wind up with a series of how every single year was different from the year before then, and fit a slope line. And that's what you see on this map. So the first thing you see is that the map has lots of white places where there is no long-term trend, where we don't have enough data to know. And you will notice that a lot of them are in the Arctic, which means we can't really actually see the particularly fast changes in the Arctic as well as we would like to. If we go back 100 years, we are doing better right now. There's also no data in the Antarctic. They started collecting in 1950 or so you have to go back a little bit less far. There's the interior of Africa, parts of the Pacific where we also are not quite sure. But if you look at the globe overall, it's reasonably well covered, and colors that are red indicate that it's a place that has been warming over the last 100 years, and blues indicate it has been cooling, and purple indicates it has been warming very fast. Excuse me. And so you can see that pretty much every place on the planet has been warming, other than this blob to the south of Greenland, which is a really fascinating area where we have a lot of variations in the ocean surface temperature that could be linked to the large scale movement of the ocean. We also have a few blobs in eastern North America, but otherwise everything is kind of warming. But if we look at how the warming has happened over time, you can see, so we have here, this is a bit of a busy diagram, and I was experimenting with getting rid of so ignore the kind of squirrely lines at the bottom and just look at the time series that is starting in 1850 and then to 1900 and 2000, and it goes to 2018, and different places, different research institutions have looked at what do the data tell us, have aggregated them in different ways, have extrapolated them further or less. So for example, the ones that are light blue, NASA GISTEM, extrapolate more into the Arctic and use more Arctic data than other data sets. But you see that overall all these data sets agree on that it has warmed over time, but it hasn't warmed homogeneously. It has warmed relatively homogeneously over the last 60 or 50 or so years, but we had another step of warming from 1900 to 1930, which fascinated me early on when I was a young postdoc trying to figure out, could we detect climate change? And I found we detected it at the end of the 1940s, and I thought that's a bit weird. So, and then in between we have this period where it didn't warm that much in the 1950s and 60s, and we have spent a lot of time debating the lack of warming in this little red blob here, this so-called hiatus of warming. If anybody heard the discussion that global warming has stopped, the whole discussion was about this tiny little wiggle in the global temperature record when it stopped going up quite so quickly and took a little break and then continued going up very rapidly afterwards. For a climate scientist, it was incredibly frustrating to hear the debate about stopped global warming if you look back on the entire time series and say, well, what do you mean? It's varying and it's warming. So, and then of course the longer term slowdown of warming in the 1950s and 60s that is probably related to pollution aerosols. So So now we would like to know, why does it do these kind of strange step behaviors? Why did it stop warming temporarily recently but has resumed? Why did it not warm so much in the 1950s? And to understand an observed record is almost impossible without some kind of model, at least a model in your mind of what shapes this record, what influences what happens. And excuse me. And so people have, for a long time, made very simple records, just simple balances based on very basic physics. If I add more energy into the planetary system, we will have, the planet has to warm. And people have also made more complex models. But the first thing we want to do before we even model it is understand what could have influenced climate to make these varying steps and hops and trends. And so, of course, the first one that is in our mind and that we have talked about in this conference extensively is the increase in carbon dioxide in the atmosphere that we have caused largely by burning fossil fuels, and that's it's one of the most famous records on the planet is the measurement of carbon dioxide in the atmosphere in Mauna Loa, and you can see little wiggles and a steady trend upwards. But the increase in carbon dioxide is not the only effect humans have had on the planet. You can see on the satellite picture, you can see the haze over parts of China that is associated with burning fossil fuels and with pollution. And this kind of haze, and I think most of you will have seen this kind of haze when you, for example, when you fly and land and dive into a brownish, whitish cloud surrounding a city. So this kind of haze is not only bad for health, but it also reflects incoming sunlight. So it slightly cools it. It's regions that are sitting under a haze like this don't get quite as warm. And that is what we think caused the reduced rate of warming in the 1950s and 60s when pollution was particularly strong in the West. In the moment, the pollution aerosols are still increasing very strongly in Asia. When we think about what other factors can influence climate, we want to understand, when you want to understand what really influenced our records, we want to also look at other factors, and a really interesting factor that will come back this afternoon, I think, in presentations indirectly, is volcanic eruptions, which are very fascinating. And when a volcano erupts strongly and explosively enough that that mass and aerosols get transported into the stratosphere, they cause a layer in the atmosphere that you can actually see in this really fascinating picture there's a picture from the space shuttle, and you can see that's the Earth at sunset from the side, taken from space, and you can see the top of thunderclouds in the deep tropics, but you can also see 3, 4, 5 layers that look dark here, and are similar in structure to the layers you just saw above from China. So these are kind of reflective layers that have been ejected into the atmosphere by the eruption of Mount Pinatubo in that case. So the space shuttle picture is taken in August, and the volcano erupted in June. And over that time period, the planet was covered in a slightly reflective haze that caused a temporary cooling. The haze or the aerosols go away in a few months, and the cooling lasts a few years. And when this happens, you have a global scale cooling. You can see it in long-term records. You also have a global scale decrease in rainfall, because rainfall is so dependent, evaporation is so dependent on the sunlight evaporating the water from the oceans. The response in rainfall is actually quite large. It responds more to things like volcanic eruptions than it responds to greenhouse gases. And so you tend to get the large rivers of the planet following volcanic eruptions have slightly decreased in flow. Dry regions get a little bit wetter. And one of the most dramatic responses to volcanic eruptions in the last few hundred years was the eruption of Mount Tambora in 1815, which caused the 1816 year without a summer that was widely written about at the time. It snowed in summer in parts of America. There was the summer in Europe was miserably cold and wet. Harvests failed, and it was one of the last times that the Western world was suffering famine. And some people even argue that the novel Frankenstein was written in response to this kind of gloomy world outside that was so cold and wet. I don't know. I don't have a strong view if it's true or not, but it was definitely a kind of a gloomy summer. Interestingly, we now also find that the combination of the eruption before in 1809 together with this really strong eruption caused a long-term cooling event that led to the glacier advance in the Alps in the 19th century. So there were around 1850, the glaciers reached maximum extent in large parts of Europe, and people were making processions and pilgrimages to get the glacier to stop going over their hayfields and destroying their villages. And the glaciers obliged and turned back, which was probably an emerging recovery from this volcanic cooling and already also a slowly emerging greenhouse warming. So we start to understand these early records, which I find really fascinating. And we'll hear about, in the afternoon, we'll hear a bit about solar geoengineering, which basically is the idea of cooling the planet by putting something like a permanent volcanic eruption into the stratosphere. When we talk about what changed climate, we need to talk about the sun. All the energy we have comes from the sun, and any change in the sun can, of course, dramatically change climate. We know that the sun is a varying planet, and it's not a planet, it's a star. It's a strongly dynamic star that has very interesting physics going on within it, and that is still not fully understood. Interestingly, the sun undergoes an 11-year cycle. So at the bottom, these kind of 3 bumps are the last 3 measured numbers of sunspots on the sun. So the diagram on the left shows you the sun at a minimum and on the right at the maximum of the sunspot numbers, and you can see that the sun has spots, and it's linked to this convection on the sun. The sun is more active when it makes spots. Even though it has dark spots, overall it's also slightly brighter. The net effect of that on a square meter on the surface of the planet is 0.25 watts, so it's not a lot at all, but it is not, so it's very hard to measure, and it's very hard physics to figure out such a small change in the luminosity of the sun, but it's definitely varying. And one of the big mysteries is how much did the sun change beyond that 11-year time scale? Did it get brighter or darker over time, and how much is it linked to past changes in climate? One of the periods that are particularly good candidates to understand this is the 17th century, when people after the discovery of the telescope started observing the sun and noticed that the sunspots were coming and going, and then they stopped coming and going. There were almost no sunspots in the 17th century. So people were really interested in what could this be, and we know from that the sun was probably less active at that time. When you look at the very, very end of the record in 2010, we also had a kind of a very slow recovery from the solar minimum that got the solar physicists all excited, and we're wondering if we are going into another grand minimum, but it didn't happen. It's been back oscillating. And there are some theories that if the sun is in a minimum, also the weather could change a little bit. We could have a tendency for more cold winters, not because of the direct effect of the sun, but of the effect on the weather patterns. That is not, so the weather patterns are highly variable, and that is actually exactly the type of weather pattern that we got in this during the solar minimum. You see, the UK was entirely snow-covered, taken by satellite. It was also quite cold in other places, and this is just one example of how the weather varies on all timescales. You all know that the weather varies and that one winter isn't like the last, and we understand that some winters or some months, the atmosphere is over the northern hemisphere has a stronger westerly movement expressed in this diagram, but it's bigger blue arrows. So it moves. The winds are stronger. They go further up in the stratosphere. The polar vortex is colder, and Scotland gets miserable wet and windy weather, and North America gets less snowstorms going into the Great Plains and the prairies, whereas if the wind is a bit weaker, you get more cold air outbreaks, you get this kind of snowy weather, you get Dallas snow, for example, 17 times more likely when you're in this kind of not so strong flow regime. We also, all of you have probably heard about El Nino. That's another example of how the planet just varies its weather, and how we cannot expect the climate warming in response, for example, to greenhouse gases to be a solid line upwards, but every year is different. Years with El Ninos are warmer than years without, and years that have a negative El Nino kind of pattern are colder. So, this is my one slightly crazy physics slide, but it's so I want to introduce you to the idea that you can actually build a computer model of the planet, which in some sense is preposterous because you can never reflect all its complexity and beauty and all the interactions that occur, so it will always be a simplification. But the general idea is that you look at a box and then you apply fairly, this box could be a box filled with air, it could be floating in front of me, and you apply very simple physical laws like if air flows into this box, there's more air inside the box. If air flows out of it, there's less air inside of the box afterwards. The only way the mass of air in the box can change is if it's either flown in or out. It can't just disappear. So if you write, you do the same thing for momentum and energy. So the energy in that box can't really increase spontaneously. It has to come from somewhere. And if you write these down, you get massively complicated mathematical equations that you can solve on a computer. And surprisingly, I'm going to show you on the next slide, that actually then behaves like the planet's weather systems, if you do it right. So you then cover the planet in lots and lots of boxes, and you can see how and you need a lot of boxes to represent it well. You think a bit about the processes that happen. You think about how clouds form, how the hot ground radiates out or heats off into space, how the sunlight comes in and heats the ground. So you have to do a bit more than just make the airflow. You add an ocean. You think about how the ocean moves by the same laws, how the salt changes its density. And then you can also simulate an ocean. And the bottom is on the bottom right, you see two simulations run in Southampton of the Atlantic Ocean. You can see in one case the Atlantic looks very coarse. Florida looks interesting, very stick-like. In the other one, you have a bit better, more boxes and a better representation. And then your model ocean spontaneously behaves a lot like a real ocean and forms a Gulf Stream, forms a hard boundary between the warm waters in the south and the cold waters in the north. So you can actually, even though it is preposterous, you can model the climate. And when the weather forecasts we look at on a daily basis are based on very similar models and use, and often the same models, increasingly the same models. And this is just an example of that it can work. So this is a high-resolution model I've snitched from a colleague, and it shows you clouds in gray and water vapor in dark blue hitting North America. I think you can maybe recognize North America is kind of on the a bit to the right, and you can see storms hitting towards Minnesota and coming through. It's a winter picture, and it would be, I think you would be hard-pressed to figure out if this is actually a satellite observation or your model. So you can model the planet. That's the conclusion from this short section. And now what can we do with it? What I want you to show is you could use this model now or these sets of models to understand why climate changed when it changed and what contributed how much. And I have a very simple illustration of how to do this. There's a lot of very complex methods out to figure out what contributed how much to a climate change in a certain period. But I show you a very simple illustration based on the IPCC report. Things you can do to determine what was important for a change is to leave a factor out that you think might have been important and see, can you still reproduce this change in your model or not? Or you can do more complex things than that, but let's do that for now. So we take the same data as here, we just plot them a bit differently. We average them over 10 years because that makes it a bit easier and less noisy. So this is the same graph. You can see 1910 to 1950 warming, flat period warming. And then you take the climate models and tell them the sun has changed a bit, volcanoes have erupted, and weather varies, but nothing else changes. And you run them through the 20th century, and the blue shadings tell you what the models do. So they warm it slightly over the early 20th century. So we have, and we now understand really quite well why this happened. We have a small warming due to a hiatus in volcanic eruptions and due to a small increase in the sun at that time period. But then when the big volcanoes of the 20th century erupt, Mount Agung, Mount El Chichon, and Mount Pinatubo, you see these little dips in the blue lines downwards. The blue line is such a wide shade because it's the 5 to 95% range of where climate models run at different modeling centers with different weather patterns at different times, what they do in response to this. And you can see overall, even without any statistics at all, that there's no way you can reproduce the warming at the end of the 20th century just with the sun and with volcanoes. If you add the greenhouse gases and the aerosols in contrast, you do a pretty decent job for global mean temperature. So to reproduce global mean temperature, you need the greenhouse gases. And even if you allow the factors to vary in its strength, or if you say the sun could be so much stronger than you think it is, and the change could be so much bigger, even if you allow the change to be bigger, you still can't explain it with the sun because you would just see the 11-year cycle and not so much of an increase. And then you can play this game, and this is a very busy diagram, and you can play this game over lots of different places. So if we just heard this fascinating talk by Sila about the Arctic ice and the Arctic. So at the very top of the diagram, you see a panel in white that has a decrease, and that's the sea ice area. So the black line is the data for the sea ice area. The pink shade is what the models do if you have greenhouse gases. They reduce the Arctic sea ice. The blue line is what they do if you don't. They don't reduce the Arctic sea ice. In contrast, in the Antarctic, there's also sea ice in the bottom left. And the Antarctic, the models don't really want to change the sea ice yet. It's too early to see a change. If anything, there's a slight increase, which has now stopped, I think, to my understanding, but there is no really, the pink and the blue lines totally overlap. You can't distinguish in a model the effect of greenhouse gases in that place yet. In North America, the temperature, right over North America, we have a box that shows the temperature over North America is clearly warmer than it would have been without the greenhouse gases. So we are fairly confident that the greenhouse gases are the big player in understanding the 20th century warming. You could now say climate has varied all over time, and it's really interesting to try to understand why it has varied and how much it has varied. And I was just listening to Sila's talk. I recognized that my picture at the bottom left of an ancient cathedral in Greenland that was built by the Vikings was actually a case of early colonialism and not just a tragic demise of an attempt to set up habitation in Greenland. So for those of you who have read about this, it's still an interesting story. So the Vikings landed in Greenland in the first millennium and stayed there for quite a while. So the last recorded thing that happened in Greenland was a wedding in 1408, and then they vanished, they just disappeared. The climate had become colder at that time. The Inuit moved further south, and adjusted just fine, but the Vikings did not adjust. And it's a really interesting cultural story why they didn't adjust, why they, it's not as simple as that they were unable to cope with the Arctic environment, but they had totally different approaches to hunting. They hunted communally. Their adaptations worked for 600 years, but didn't work after. So they vanished. And they are a sign that, or a visual evidence that climate has changed, for example, in Greenland, from a slightly less cold, it was always cold there, but slightly less cold, medieval optimum period up to, or not optimum period, up to the Little Ice Age when it was unbelievably cold, and the Vikings vanished. And we had pictures such as that on the right-hand side, showing these really cold winters we had in Central Europe at that time as well. And so I was always fascinated trying to understand why did these changes occur, but we can now understand quite well why they did. So if you are into busy line graphs, the gray shadings, the many gray shades are attempts to figure out from tree rings and documentary records and ice cores what happened from 1400 to 2000 onwards. So every green line is one person's reconstruction scaled with another person's favorite calibration method to the instrumental data, and shows what could have happened. They all agree that it was really cold around 1815 when the big volcano erupted. They all dipped down quite deeply. That's one of the coldest periods in that timeline, but you can also see that they dip around 1600. And then the colored lines are what happens if I take my model and just run, for example, only the effect of volcanoes in that time period. We know when the volcanoes erupted because we have historical records, and the volcanoes dropped some material on the ice cores in the poles. So you can look at ice cores that Richard Ali showed us many pictures of, and see if there was evidence for a volcanic eruption at some given point in time. And so the brown lines, actually, I would argue that the brown line trails the gray line reasonably well, and the volcanoes were a big player in causing cold periods in parts of the last millennium. A player that the first speaker of the conference has mentioned is greenhouse gases. The red line, if you just squeeze your eyes a bit, you might think that the red line is a little bit lower, 1600 to 1700. Greenhouse gases were a bit lower in that time period. We don't understand why. It could very well have been the deforestation of the Americas following the extinction of the native population by the colonizers. So we could have even then had a small greenhouse effect with contributing to the cooling in the Little Ice Age. So we begin to understand why climate has changed over the last millennium, and we can understand many of the episodes that happened and find that volcanoes and CO2 are bigger players than the sun. We can also see if the hypothesis that the sun could have been a huge factor varying varying in a very large term, we can evaluate that hypothesis and find that it does not match the data. When we think about climate change now and climate change in the future, the biggest concern we have is extreme events. This is a picture of Katrina heading for New Orleans. We know that tropical cyclones or hurricanes are really hard to predict how they exactly respond to climate change, to global warming. We understand, though, that if you have warmer sea surface temperatures under the exact same hurricane that has already formed, then you will make it stronger. If you have rising seas, and you have a storm surge, then there's just a bit more water to come inwards. If you have a moister, warmer atmosphere, there's more moisture available to cause heavy rain, to rain down and cause flooding. This at the bottom left is the cyclone in Mozambique. In the last year, we had the wildfires in California. Fire is incredibly complex, but there is a tendency in areas where we think the data are somewhat homogeneous, like parts of Canada, that if you have a warmer year, you have more fires, more area burnt. So while it is really complicated to say why it's burning right now in this place, overall it burns a bit more when it's hotter. And on the right-hand side, I apologize for this photo because I think it's so sad. It's the But I really want to show it because it shows us the limits for the adaptation of animals and humans. So these are the flying foxes in Australia. They die when temperatures exceed a certain threshold. Their little bodies cannot cope with that, and they just fall out of the trees and dies. And that happened in a pretty big time in one of the recent heat waves. So they cannot adapt to heat that their bodies cannot cope with. And I think we humans shouldn't forget that we are also animals, and we will be in the same boat if it gets too hot. And some places, under the very strong warming scenarios, might get so hot that people are in danger outside. A period when it was super hot was the Dust Bowl in the 1930s. That is also a warning period for me. What happened, so we had record-setting heat waves, and we still haven't beaten them. And what happened was that there was a strong drought. There was changed land use, so people plowed up the great prairies and started growing wheat. The wheat brought in really good money and was selling really well, so more got plowed up. And then the drought got the farmers in trouble, who had to plow even more to try to break even. And so there was a huge, very fast change in how the prairies were used. And then the drought killed the crops, and bare soil was exposed. The soil was blown. The vegetation died, and this is implicated in the record heating. In our model, when we actually just remove the grass and replace it by bare soil, we can get very extreme heat. So this is a bit of a warning, because if the effects of climate change affect vegetation, we can have interesting feedbacks that we really don't want. I think I'm already kind of pushing my time here a bit. If we don't reduce greenhouse gases, we will have 4-ish degrees warming by the end of the 21st century. This is uncharted territory. It's uncharted heat waves and very dangerous. In my personal view, if we try to address climate change, that's a diagram from the report that came out that Diana talked a little bit about, the 1.5 degree report, and it's a very busy diagram. It just shows you how the observed temperature record continues dependent on how we address climate change, and various attempts to limit global warming to 1.5 or 2 degrees are shown. And for example, if we reduce methane emissions that are linked to meat consumption, it's a bit easier to meet the target. If we reduce emissions faster, we don't overshoot quite so much. What we have to do, and that's why I'm showing you this diagram, what I'm really concerned about is the bottom left of this slide. This shows the emissions in CO2 over time. To 2100, it shows you the line where we are right now. It shows how they have been increasing and increasing and increasing. And the gray and the blue line shows you what we have to do to keep warming under 1.5 or 1.5 degrees. And you can see a really dramatic change in emission patterns. So we have to very quickly change our emissions from continuously up to down and net zero by 2050. And I think this is really hard. And I'm a bit scared if we can actually do this. We have to do it in a way that doesn't crash the economy, because nothing goes right if the economy is in a bad state. Believe me, as a German, I have read a lot of history in Germany, and I think the very bad economic situation in the 1930s certainly contributed to the rise of extremism, with all its really horrible consequences. So we don't want to push the economy over the brink, and the Working Group 3 has estimated that we can do this turnaround. We can even benefit from it in human health and stuff if we do it right and if we do it reasonably soon. We have to make some hard decisions. Doing this step change is much easier if we have some nuclear power, if we capture the emissions from some coal-fired power plants while we transition. We don't seem to, but those are both hard topics. There is some discussion to what extent we should employ geoengineering. We'll hear about this afternoon. That will be an interesting debate. I'm personally not so sure, but so we will have a great debate. I'm looking forward to that. Because I'm concerned about the rainfall effects of volcanic eruptions and geoengineering. But what we can do at this point is just really recognize that this is serious and that we need a global solution. So we need the countries of the world to agree on a plan. Otherwise, the people who push forward quicker might get economically punished, although they might also have an advantage by pioneering new technologies. And one thing that I really want you to recognize is that many developing countries have contributed really little, but are the ones that are hit first. So the Arctic is very sensitive due to the sea ice, but also a lot of the tropics. In a lot of the tropics, the change by climate change is much more unusual compared to the normal weather fluctuations than it is in our latitude. So the people in the tropics experience aspects of climate change stronger, and they have contributed less. And so that sets them on the move, which bridges back to the first talk. So yeah, I think that's as far as I wanted to go, yeah. Any podium now?